Hello, I'm Danny Webster from Light Microsystems, and I'll now be talking about advanced digital radio systems. So, first thing we're going to look at is detecting and reducing data loss. We're then going to look at spread spectrum radio for extreme range, and then look at the very popular OFDM radio system, particularly focusing on 4G. So as I mentioned in a previous presentation, from 1991 there's been an explosion in radio standards. So we're just going to concentrate on 4G and 3G today. I appreciate that a number of other systems have attracted a lot of interest, but we'll keep it simple today. So the first thing is reducing data loss. So noise leads to data uncertainty, and we need to be able to detect errors through parity and CRC. We'll look at error multiplication through encryption and data compression, and then we'll look at error reduction through error correction techniques. So if you speak to a digital engineer, he will tell you that a binary signal is just 1 or 0. How can you mess it up? But once you put it through a real radio system, the signal becomes rather more interesting. So we have a signal which is now a probability density, and we have some sort of decision threshold. And as the signal approaches the decision threshold, we become less and less certain about how accurate that signal is. So it's highly likely that at some time our radio signal will contain some sort of error. So we need to be able to detect this error. So there's been a number of error checking techniques. The most simple one is the 8-bit parity check, which is just really a modular sum of all the bits. And then there's the more complicated CRCs, the cyclic redundancy checks, which use a polynomial-based technique using shift registers and modulo 2 arithmetic. And then on top of that you have handshaking protocols built into the radio techniques. So you detect whether the receiver has received a problem, and if he has, you then retransmit. And it gives you a way of checking the quality of the link, and if necessary you can change some of the link parameters to improve reception quality. So let's have a look at what happens when we begin to encrypt data. So a very popular way of encryption is to use what's called block encryption, such as DES64. So we'll look at a very simple block encryption here, based on the alphabet and the magic square. So initially we have a set of alphabet which is in alphabetical order, and then we scramble the rows and columns to give our encrypted data system. So for an L we substitute a J. So what happens if we look at the ASCII of J and introduce a binary single bit error here? It becomes a K, it's mutated, and this K is then deciphered as an S. So when we compare S with L, we suddenly find we have 5 bit errors. Even though the link only had 1 bit error, the encryption and decryption process has multiplied the number of bits of error we have. So this is a common problem in all the block encryptions. An alternative approach is what they call a running cipher, usually based on a pseudo-random sequence or a gold code, which is exclusively or modulated onto the signal. So these are generated by shift registers with modulo 2 arithmetic, and they're commonly used in things such as 3G, 4G, GPS and Wi-Fi and so on. The pseudo-random sequence can be over a single frame or even over multiple frames. And it can add randomness to repetitive data systems. So if you have a telemetry system always transmitting zeros, this will actually reduce some of the difficulties in using that signal just by deliberately scrambling that sequence of signals. Another thing we want to do when we're using a radio link is to actually compress the data. So we use less bits to transmit the data than to actually use to represent the data. So we're very familiar with these techniques these days, such as MP3 and MPEG and ZIP and so on. We often see these on our personal computers. And these are based on the FFT and Huffman coding. And the idea is that we can somehow simplify the signal and then transmit less bits. So let's have a look at a very simple example now. In a language, we commonly use about 400 words, and then there's about another 10,000 words which we use only occasionally. So if we think about the ASCII code is only 7-bit long, so it's 128 codes, but we normally encode this into an 8-bit word which has 256 code values. So we have 128 spare codes. So let's use some of these 128 spare codes for 128 commonly used words. So let's define our dictionary here. So 128 the, 129 and, 130 now, 131 don't, 132 feed, 133 kill, 134 cat. So I can now write a sentence and feed the cat. It's now 4 bytes long. So it achieves a compression rate of about 400%, so fantastic. So let's introduce a 1-bit error into this code. So for example, if we change 129 to 131, we get don't feed the cat. If we change the second number from 132 to 133, we now have and kill the cat. So suddenly our message has gone from something fairly harmless into something that's life-changing, has life-changing consequences. I'd like to reassure people that no cats were harmed while we made this slide. So the next problem we have is that we know we're going to get errors in our link at some point. So is there any clever way we can actually correct these codes? And the answer to that is yes. There's hundreds of error correction codes out there. One of the simplest is the Hamming code, which consists of a identity matrix which transmits the bits that you want, together with a selection of parity codes. And then using some clever mathematics, you can then check whether an error has occurred in the code and then correct a single bit error. Obviously there's many other more sophisticated techniques such as Reed-Solomon used in CD technology, Viterbi codes which are widely used in mobile communications, and more recently turbo code and low density parity checks are used in 4G and in digital TV. One of the properties of error correction techniques is that they often work well when there's a relatively low error rate. But if you have a burst of errors, then these techniques begin to fail. So what you tend to do is you interleave the data. So for example, swapping rows and columns, you can change a burst of errors into a sequence of single-bit errors in successive words. And this greatly helps the error correction process, and you will find this in many of the widely used radio standards such as Wi-Fi and mobile communications. Another property is the effect of bit errors on high density modulation. So I think just by inspection, if you look at QPSK, you can survive a fairly large amount of noise and still receive the signal undamaged. Whereas if you had the same amount of noise on a QAM64 signal, the signal would become completely useless. So let's have a look at the QAM16 case. If we were to number the points in the Cram constellation in a simple binary fashion, what we find is that going horizontally or vertically, we can have up to 2 errors, and then going diagonally, we get up to 3 bits of errors. If we were to change our coding into a grey-coded numbering system, what we find is that we only get 1 bit error if we jump into the adjacent constellation point, and we only get 2 errors if we go into diagonally connected constellation points. So just by changing our numbering system, we can reduce the effect of bit errors on a Cram symbol. Another popular technique is what's called soft error correction. When I talked previously, I said we could talk about our digital noisy signal as a probability. So if we're out here, we're pretty certain we had a 1. Whereas if we're here, we're pretty certain it could be a 1 or a 0, it could be either, and we have no way of telling. And then if we go over here, we can be pretty certain it was a 0. So if we could feed that probability into our error correction algorithms, then we can design a more constructive error correction technique called soft decoding. So we have an idea of which bit contains the bit error rather than being equally probable. And when we apply this, we find that the error correction technique improves 1 or 2 dBs. So here is an example with a Hamming code, and you can see that we achieve an extra 1 dB, maybe 1¼ dB improvement in the EBN0 of the technique just by going to soft decoding. Another technique widely used is convolutional error correction, and the idea here is that the parity codes generated are actually dependent on the history of the signal. So you're not just looking at one word in isolation, but you're actually looking at a sequence of words. And then if one word is corrupted, you can use the history to recover the signal. So you end up with these sort of trellis deconvolution diagrams. So the blue signal here is the intended code system, and the magenta path is the decoded system, and the red is other possible solutions which are being evaluated. And basically you can put Hamming weights to each of these paths, and then you can work out which path was the most likely for a situation. One of the nice things about the trellis decoding is that it actually converges. So even if you have a sequence of bit errors, the signal will then come back and you can then start processing the signal as normal. So again, you can do hard and soft Viterbi decoding. So in our simple example here, we have a few bit errors, and that leads to 3 errors in our final recovered signal. So you can see the divergence and the different pathways. And then with soft decoding, we managed to recover all the bits with no bit errors in this case. So one of the things we have is that there's a compromise between our ability to correct errors and our data efficiency. So if we think about the Shannon-Hartley theorem, we can express capacity as being related to bandwidth and signal-to-noise ratio. If bandwidth is fixed, then our signal-to-noise ratio change leads to a change in capacity. So the easy way to think of that is that if my signal-to-noise ratio is degrading, I need to add extra bits for my forward error correction. What happens in mobile radios is that the signal strength is actually changing with time. So sometimes I can use a very weak error correction code and get lots of data transmitted, and other times I have very poor signal strength, and that leads to a lot of errors, and I need to use a strong error correction code. So what we need is actually adaptive error correction. And this is done usually by a technique called puncturing, where you throw away some of the bits from the error correction code, and then you allow the error correction code to then replace those bits at decoding. So let's have a look at spread spectrum signals used in WCDMA, which is 3G. And we're going to look at it from a slightly unusual angle. We're going to look at it from an error correction point of view. So we're going to introduce spread spectrum as an error correction code. We're going to look at autocorrelation functions, multiple access channels, long-range transmission, and at some of the typical 3G signals. So another way of looking at the Shannon-Hartley theorem is that if I choose to keep capacity a constant, but I degrade my signal to noise ratio, then I need to increase the bandwidth of the signal. So imagine that I got the same information, but I'm increasing the transmission rate to accommodate my error correction code. We can call this spread spectrum. So what happens if we go on increasing and increasing the bandwidth? Well, eventually we find that we can decode the signal even if it's below the noise floor of the system that we're actually using. So let's have a look at an example. BCH 637 code. We have 7 information bits and 63 transmitted bits, and we can correct any combination of 15-bit errors. We had spread the spectrum by a factor of 9. So then we can ask the rather dumb question, well, what if I forget about all this error correction coding and just send the same message 9 times? So we substitute 1 with 9 ones, and we substitute 0 with 9 zeros. And it turns out we can correct 28 bits of error at a rate of 4 bits per symbol. We have a code gain of 9.5 dBs, and this gives us an EBN0 from 7 dBs down to minus 2.5 dBs. So we're now actually receiving a signal below the noise floor, just using a very simple 9-bit code. Instead of using 1, 0, we're going to use 1 and minus 1. So now decoding is an exercise in pattern recognition, and we can use the autocorrelation function very effectively to determine whether we received a 1 or a 0. If we use all ones, we find the autocorrelation function has a linear slope like this. But if instead of using all ones, we use a pseudo-random code, we get these sharp points. And this means we can start using the autocorrelation function to measure phase shift and small Doppler shifts, and also detect the presence of echoes. And so we can then use the autocorrelation function response to design echo-cancelling FIR filters. What if our signal is no longer thermal noise, but actually the noise of other signals in the same bandwidth? What we have then is a code domain multiple access signal, where we transmit each signal on a separate spreading sequence. So let's have a look at a 3G signal where we have 128 spreading codes, and we're using 64 simultaneous channels operating at the same time. So we can use spread spectrum signals for very long range signals. So for example, a WCDMA uplink would use typically a 1/4 watt power. It would have 24 dB code gain under the lowest data rate of 15 kilobits per second. And you can achieve something like a 20 kilometer range with a 30 dB margin, assuming a receiver sensitivity of minus 120 dBm. Similarly, we can look at a GPS system where you have a 20 watt transmitter. You have a code gain of 43 dB, at 50 bits per second. You have a 25,000 kilometer range with a receiver sensitivity of about minus 130 dBm. So let's have a look at the WCDMA downlink signal in a bit more detail. Basically, we have a variety of control and data signals all being added together, each one being multiplied by a Walsh function which is used to orthogonally spread the signals. And then we have a pseudo-random sequence here to give privacy of the signal and to help with frame synchronization. And there's some alternative synchronization signals added at the end. And then the whole signal is root raised cosine filtered. So here we see a 3G signal being generated with a LimeSDR. So we have the downlink signal here being displayed in octave. And here we have the uplink signal also being displayed with octave. And here are the same signals on an Agilent spectrum analyzer with a 3G personality demodulating them. And you can see the EVM figures are typically about 2 or 3%. An alternative approach to CDMA is frequency hopping. The idea in frequency hopping is that you would have an interference on a particular frequency band which may be moving in frequency. So for some of the time your signal will be in a region where there's no interference. Some of the times your signal will be in a region of interference and is lost. And in some of the time your signal will be in a place of multipath fading and the signal is lossy and you'll have some bit errors. Providing we spread the data over the entire frame, the error correction system will then recover the data despite all these adverse propagation effects. And this has been used in systems such as Bluetooth and to some extent is used in 4G. And again, it's used in Wi-Fi. The idea is that the spread sequences of the different users are not correlated. We will still get some crashes, but nevertheless the system is usable under medium density traffic. So now let's have a look at OFDM. We'll look at the OFDM spectrum. We'll talk about how to equalize an OFDM signal. We'll talk about the cyclic prefix and echo cancellation. We'll talk about peak to average minimization. We'll look at the resource block map of the 4G signal. We'll look at frequency hopping in the 4G signal. And we'll look at MIMO. And we'll look at the 4G physical layer. So as we've seen, we can use one large signal, such as spread spectrum, or we could use many narrowband signals which are somehow related to one another. So in OFDM you have subcarriers which are regularly spaced, which are modulated. Some of the subcarriers are not used, for example 0. This removes the need for calibration at the 0 frequency. You can use some of the carriers for synchronization or pilot tones. And you can use some of the subcarriers for QAM, for data transmission. And they're generated by an inverse FFT process. The idea of pilot tones is you have tones with known amplitude and phase. And then basically, if the signal goes through a global phase shift, you can use the pilot to restore the phase of the whole signal. And if you have a frequency-dependent phase shift, you can use interpolation to recover the data signals. Another technique used in OFDM is to add a copy of the end part of the symbol at the beginning, and this is called the cyclic prefix. And the idea is that if your echo is within this cyclic prefix, then the idea of superposition holds. And what that means is that your signal is a sequence of sine waves, and your echo is also a sequence of sine waves, and adding those together leads to a small phase shift, which then the equalizer then corrects. So you don't need to use a rake type filter you had to use in 3G to recover your signal. One of the difficulties of OFDM is that if the carriers were somehow all coherent together, this leads to a very high peak to average ratio. It's very similar to the sync function. So you get a big peak at a certain period of time, and then the signal becomes much smaller. So that's when all the signals are coherent. For a normal signal, the signal is randomized. So for example, you would use a spreading code on your pilot sequence. So you're no longer transmitting a coherent set of pilots, but a phase modulated set of pilots. Or alternatively, you can use a Zadov-Chew type sequence, which is more like an FM chirp. And both of these lead to a reduction into peak to average ratio of the signal. And what this means is we can use a lower power transmitter to transmit the same information. So let's have a look at some 4G signals generated with the LimeSDR. And you can see here we have the downlink signals, and here we have the uplink signals. You can see that we have a mixture of we have a mixture of pilot tones, control codes, and various synchronization codes, as well as the 64 CRAM and 16 CRAM data traffic. And likewise in the uplink we have a similar set of signals. The uplink signals tend to use what's called SC FDMA, which is a pre-coded version of the OFDMA signal, which reduces peak to average ratio. Okay, let's have a look at the 4G signal in the resource block map. So here we have the downlink signal, and here we have the uplink signal. So the downlink signal consists of a set of control signals, a set of pilots, which you can see in the blue here, as well as synchronization signals and some global system messages, and then the rest of the traffic is transmitted in the remaining space. In the uplink signal, the signal is generally simpler in some respects. You have the control signals on the outside edge, and then you have the data traffic in the middle. And again, you can have multiple channels here, mixed either in frequency or time or both. So frequency hopping is very easy to do in OFDM. You just shuffle the resource block allocation around in different subframes of the signal. So let's have a quick think about MIMO now. I think the FM stereo system many of us grew up with is perhaps the simplest form of MIMO communication. The idea is you had your left channel music and your right channel music, and then you modified them by combining some of them and subtracting some of them to produce two sets of signals, the left plus right and the left minus right. And then these were modulated onto RF using a 19 kilohertz subcarrier pilot. So a simple low-cost FM receiver just concentrated on the left plus right. A more sophisticated stereo receiver would demodulate both halves. And again, the demodulation process was a matter of adding and subtracting the two signals. So in MIMO communications, you're using multiple channels. The idea is that the Shannon-Hartley theorem says there's limited capacity in a particular channel. So the way around this is to have more channels. And what you have is what's called spatial diversity, where you use multiple antennas transmitting different signals. You're then using the DSP at the other end to differentiate signatures in each of the MIMO channels to uniquely identify each MIMO channel and to separate it from the different combinations received by each antenna. One of the advantages of MIMO is it allows us to carry out a crude form of beam steering, so we're actually able to target some of the spectrum of the transmitter to different receivers in the field. So we're now going to have a look at the 4G downlink physical layer, and this is quite a complex system. Initially we start by adding the cyclic redundancy codes to the data streams. We then add forward error correction, either turbo or Viterbi encoding. We then interleave the data streams and collect the bits together, and then apply a scramble code to the data streams. The data streams normally go into the shared channel, but there's also a number of additional channels used for broadcast information, and also various control channels for controlling the link. And on top of that, we also have the reference pilots and the 2 synchronization codes. This data is then produced into a resource block map of the frame or the subframe, and then using a sequence of fast Fourier, inverse Fourier transforms, we generate the pulses to go through the 2 MIMO channels. The 4G uplink physical layer again is very similar. We had the cyclic redundancy code, we have the turbo encoding for the forward error correction, the interleaving, the scramble code added to the sequence, and then we have a mixture of the shared uplink channel and then the various control channels and synchronization channels. And then these are then decomposed into resource block maps for the 2 MIMO channels, and inverse Fourier transforms and cyclic prefixes are added to each of the MIMO channels before sent to the USB and the LimeSDR.